Morning, everyone.
Hi.
Hey, Yasser.
Hey, I'm not on schedule, but I'd like to give an update for the stuff I talked about for weight interface and tracing.
Okay, sounds good. We'll give a couple more minutes.
Why, Feng, do we know whether Jack is joining?
Sorry, what is the question?
Do we know whether Jack is joining?
Oh, Jack is has a doctor appointment, so he won't be
Does
able to
he?
join
Okay,
today.
okay.
Yeah.
All good.
Can you guys see my screen?
Yeah, I can see it.
Okay. Okay, so maybe we can get started. So as I just mentioned, Jack has a doctor appointment, so he won't be able to join today. So I'll be hosting this session. So Jack sent out the agenda for the week. So I add a couple items here. So first one is about a quick summary about global summit submissions. And Victor also mentioned that he's has some topic, so we'll add that to the end of the session. Here I just want to basically really bring this to everybody's attention. So from an AI co-design perspective, we do have a bunch of proposals submit to this so-called AI server breakout session. So it's highly selective. Good news is we do have like 2 submissions got accepted. Let me see here. So as you can see from OCP website, there was the first one, enabling macro heterogeneity through a system of systems approach, and also YASA has one from a workload algorithm perspective. And we also have a few other submissions, and because they are either merging into the existing some of the agenda related agenda topics, or it's just due to limited space. So, but at least from our submission, we can see that the quality of the submission is pretty good. So congrats to the one who got accepted. And in addition to this breakout session, OCP also has a Future Technology Symposium, FTS. I saw a few people submit from to the FTS, although they are not directly part of this co-design work group, but the topic is very close. You can see here, I do see Tusha got some kind of a simulation related work accepted in the AI HPC session. Yeah. I don't know if this FTS is also published, but at least you can see the breakout session. It's already scheduled with all the details. So anyway, congratulations to everyone. Oh, oh, oh. Think I got that closed for some reason. So I'll just follow the agenda, basically walk through some of those updates from the work stream. As everyone know that at the beginning of this work group, so we set up a few work streams, and this will compose the main components of the our work for this year. So I don't know if Kevin is, because I cannot see people in the list. So is Kevin in online?
I don't think so, actually. No, I don't see him in the meeting.
Okay. I know that there's a few topics related to BOW, chiplet, and also neuromorphic computing. I know Hisham organized quite a few external kind of meetings talking about the neuromorphic. But at this point, we don't have a very clear agenda for this neuromorphic computing at this point. I don't know if Hisham, you have anything to updates?
Yeah, so this week actually we had a call or a presentation from Brain Chip about their ASIC and FPGA implementation of neuromorphic computing, and it was very well attended meeting from different groups in OCP. And because some of the attendees asked really deep technical questions, so there will be a follow-up to this meeting with the CTO of BrainChip. I think by at this point, given all of those presentations from external experts and different in academia and industry, we should have a clear idea about how we can use neuromorphic computing in our design of AI systems, because that's exactly what those guys are doing. But how we can do that in this group, that's what we need to discuss. And Jack said he will hold a meeting with few interested people in this group to discuss next steps moving forward. But
Mhm.
he didn't have that meeting. Maybe he's busy. I don't know why.
Yes, I know there was quite some discussion through the email threads or even for inside this online meeting. At this point, I do see people interested in this topic, but there was no clear agenda or goal for
Yes,
us at this point yet. I don't know who is driving this, trying to maybe.
you are right. You are right. You are right. And to address this issue, Jack said he will take the lead in having a meeting with interested people to answer these questions. What do we do with it? How we can move
Mhm.
forward? And he suggested to start even a white paper. He sent an email about it, to start a white paper and see who's going to contribute to it. And so he's taking the lead on this stuff to move it forward. But in the last 2 weeks, he didn't do this. And maybe he's busy. I don't know.
Okay, I'll check with Jack, but
Yeah, exactly.
we
Exactly.
do need to have a clear action
You
because
are right.
at
You
the
are
end
right.
of the year, so we need to basically provide some kind of a progress update to OCP.
Yes, you're right. And Jack is supposed to take the lead to make that happen, actually.
Okay, I'll check with him.
Yeah. If he would like me to take the lead and take it over, I can do it. But for now, he is the one who's coordinating the work with different people who expressed interest in this topic.
Okay, so
I think Hashem, if because you said that you could do it if he's busy. I think Jack, because obviously he's been doing quite a lot of organization with the group, and I know that he's looking into the data services side too. If
Yeah.
you have time, I think it'd be great if you could take that lead on that. I think he'd really appreciate that.
Okay,
yeah, that's
let
what
me
I
talk to him.
actually am trying
Sure,
to
let
say.
me talk to him. I don't want to step on anybody's toes. So if he would
I
like
don't
me
think
to
you
do
will.
that,
I think he'd really appreciate it, honestly.
okay, okay. So who is this?
Yasa, just
Oh, Joshua, how are you?
Good thing.
You are one of the people, actually, he said in the email he would like to talk to you about it also.
Yeah, I'm happy to come along if you take the
Yeah,
lead and organize the meetings. I definitely have some opinions on the matter, but obviously I'm very focused on driving our algorithm work forward. So
okay.
I, can't take the lead on it myself, really.
Yeah, no problem. Thank you very much, Joshua. You are
No
also a
problem.
knowledgeable guy in this area.
okay. So Hisham, I'll put you a name down for initiate this effort, trying to basically provide overall framework and maybe potential actions, and also
Sure,
the
sure, sure. Thank
the.
you very much. Thank you.
Okay, that's great.
Thank
And then we can move on to the second one, compute model from Yasa. You can provide update for us.
Yeah, I got a little couple of slides for you guys, but I think you
Okay,
need to unshare your screen so I
okay, sure.
can run you through that. Let me see. Here we go. Wait, which one does it do now? Quickly checking. Okay, should be this one. Share. Oh gosh, privacy settings, of course. One sec. Oh, what's going on? Okay, I'll quickly sorry, very unprofessional. I quickly have to reopen Zoom. Something must have happened. I'll be with you in a minute. Either maybe I think Keysight team is here. Maybe you can start and I'll take the second slot if that's okay. I'll be with you in a minute.
Okay, that's okay with me. Am I audible?
Yep, go ahead.
Okay, so based on this preview, by the way, this is King Shuk from Keysight. And based on the feedback that we have in our previous meeting, we are taking 2 concrete action on our side. The first one is about we are coming up with a refined version of the schema to address some of the questions related to networking, related to, I'd say, some confusions regarding terminologies, relationship between components and etc. to those things more clear. And we will be working on that in this next week and maybe a little more than next week. But in the process of doing that, we are reaching out to Prakash and we are looking for a slot to meet with him in a smaller setup to get more of his comment. He has many good questions and suggestions in the previous meeting, and we just wanted to have a follow-up with him. So we are intended to do that next week. And the second aspect on which we are working is, again, based on the feedback that came in the previous meeting, that's from Jasha. There was a lot of good questions related to hierarchy, and it was not very clear how hierarchy is currently addressed. So we got an example from him, and that is through email interaction with him. And we'll be working on that as well. We will try to come up with his example that how we can model in the present schema, or the schema is insufficient today. Then if it is insufficient, what else we need to bring it in. So these are the 2 activities we will be doing in coming 2 weeks. So that's what is the update from Key side.
Okay, so you did mention that you got an example from Yasa. So the main idea for this hierarchical representation, basically we want to using this schema to represent those type of like a fractal kind of a computing. So very similar to those kind of OOP type of programming language. So you can kind of stack up all those hierarchical components so that you can either zoom in and zoom out to see like a different level of details, right? That's kind of idea.
Well, first is we want to represent the hierarchy. Now, how much of this hierarchy we will zoom in or zoom out, it is up to the applications. We want to see that the schema is capable enough to describe a deep down hierarchy to the leaf level. And now representations is up to the tool. The tool might say, okay, I have the full schema, but I'm right now giving you a view of a section of it, which is a hierarchical view from the view perspective. And then if you want to zoom to a particular section, you zoom in further, and the schema feeds you the zoom in information in terms of, I would say, data model and the relationship. So it is the tool. If tool is the visualizer, and the schema is who has got the detailed description, and it is up to the visualizer which section of the description it is showing at this point of time, which section it is zooming in, and in which section it is zooming out. So that's the tooling part. So first we want to finalize the schema. Yeah.
Sure. Yeah, maybe you can just work on those example first. If the schema itself has the capability to represent that kind of hierarchy, that'll be great. So we can start with that.
Sure. And in fact, I will also reach out to you if you have another example. And the more examples we get at this stage, the more refinement we can bring in the current proposal.
Sure, sounds good.
I comment.
Yes, go ahead.
Yes. Well, first I have to acknowledge I totally understand how difficult it is to come up with these methods and methodology to describe large systems. We've had similar conversation as part of composable memory system work group around memory fabric orchestration, which also include many components coupled together through switches and links and other things. The team has started thinking about how to enumerate, how to discover, and how to manage for the sake of component management and then fabric management. So a model people have started using has been DMTF's Redfish, just to name things, just to demonstrate hierarchies and such. So I'm wondering, for the sake of discovery management and fabric orchestration, as compared to for the sake of efficient data movement. There might be different reasons for different viewpoints, but if we can use similar semantics, similar nomenclature, and similar methodologies, that would help everybody at the end.
Yeah, understood. Yeah.
So are you working with the MTF and Redfish schema concepts?
Not yet, but I'm taking a note of it to understand this DMTF and Redfish with little more detail than what I understand it today. But yeah, we'll definitely take a look. I'm taking your input.
Thank you very much.
So that's all from my side.
Okay. I hope Yasa is ready.
Yeah. Well, we'll try
Okay.
this again. Sorry for that. Okay.
No problem.
Okay. Now this seems to be working. Do you see my screen? Slides?
Yeah, we
Do you see
do.
slides?
Yep.
Good, cool. Okay. Yeah, quick update from me and obviously Dan. We're obviously leading the algorithm part of this work stream together. And now this is also preparing a bit towards the OCP Global Summit presentation. Obviously, we're very happy that we got one of those slots. So I'll run you through like roughly what we've been up to throughout the last month and a half, I guess, 2 months. So the way, maybe to give you a bit of a framework, the way that we started thinking about this is, for co-design, generally speaking, and obviously that then applies also to the algorithms that guide co-design, we think about this as happening on multiple timescales ultimately. So, I like to come on at this sometimes with a bit of a kind of neuroscience, cognitive science inspiration, but ultimately, if you think about how systems learn and adapt, there's multiple timescales to how this happens. There's kind of a very quick, short inner loop, and then you adapt to like on very short timescales and maybe tweak kind of smaller parameter range, and then obviously as time goes larger and you optimize for a larger set of tasks, there's longer timescales. So in order to bring this to the idea of co-design, we can think about the spectrum where like on the slowest to change is obviously the hardware architecture, then maybe the algorithm architecture. So the general, is it a transformer? Is it a state space model or something along those lines is a bit faster, but still quite slow. And then there might be parameters within the algorithms which are a bit quicker to change. And then ultimately the quickest thing to change is probably deployment strategy. And so what we're trying to cover on the algorithm side of the work stream is essentially more, well, we're hoping to touch all of these things in one way or another. Obviously, shallow to begin with probably, but the way that we think about this is on the one hand, we want to create algorithms that can fine tune both hardware and algorithm architectures over design cycles. So this is what we probably think of as the classical spectrum of co-design. So more on the kind of left-hand side of the spectrum, and then meaning on the slower side of the spectrum, and then on the faster side of the spectrum, we want to create algorithms that can respond to changes in the workload and the system state on very short timescales. So then we ideally want to cover both of them, and I'll elaborate on this a bit more on the final OCP presentation. Obviously, today is a shorter update, so I'll run you through like roughly what we've been up to. Ideally, obviously, or in the end of the day, how this usually works is they influence each other, right? So there's this kind of loop. You learn about slower changes, and then you also learn what can change faster, etc. So you can have this nice little feedback loop here built in. So on the spectrum from fast to slow, I'll run you through like 3 things we've been doing. The first thing, right in the middle of these, is a new hardware, is a new algorithm architecture that we've been working on. We call this mixture of pathways. So actually, you can find this online now. I'll update the slide. The slides will be on the OCP drive after this, so you can also access it there. But if you're curious, right now, you can scan the QR code. If you can't wait for the slides. But essentially, what we've been working on there with a student of ours in the Oxford group, Jack Hook, is we've been working on this new mix of expert architecture, and not enough time today to go into the details, but to give you a high level idea. This is kind of aligned with maybe what you've been seeing in the context of DeepSeek et al. It's essentially an algorithm which is made up of little subparts and subnetworks, and we specifically build it up in a heterogeneous way. So the different experts which are in this model, so the different submodels that are contained in the larger model, they have different sizes of computational complexity. So there's very large ones which are very complex, can do very complex functions, but those are very simple ones. And so the idea of this overall architecture is that it can use the different combination of these models to adapt to the current situational complexity in the first instance. So that's what we've been working on so far. So we've built this model. We found that by default it doesn't actually work. So we had to come up with this custom loss function. But then once you have this nice custom loss function we've been working on, you can see that the model overall allocates more compute capacity for tasks which are more difficult. So, you know, the plot to read this is like task difficulty is on the x-axis, and then on the y-axis there's amount of compute that the model spends to solve the task, and you see there's this kind of positive correlation here essentially. So the nice thing about this architecture is that this can now adapt to current workloads essentially, right? So this is kind of our kind of first way of having an algorithm which can adapt to the current situation and the current hardware at the same time, right? You can see that the cluster which has more large-scale capacity maybe can rely more on the complex experts than the simple ones, etc. So it's a nice kind of algorithm framework for this co-design environment. So we have this this algorithm overall running. The reason why we think this is a nice way to fit into this co-design cycle is we can now look into what we call dynamic deployment algorithms. So we have algorithms which can actually, in a sense, design the setup you're currently running as a function of your current algorithms and system state. So ultimately, what we want to achieve, we want the compute that is utilized by your underlying HPC system to be reactive and state dependent, in a sense, what we call this. But we also want to have it regular and predictable. This helps deployment ultimately on the HPC architecture. And if you're curious why that is, there's this nice little reference here on expert flow. So these are the two different features we've set ourselves now to expand this model towards to help dynamic deployment. So that means that it can react and adapt the deployment to the underlying hardware system. So the regular and predictable part of this is ongoing work. I think actually Gabriel's on the call. He's a student who joined the lab recently and is now helping with this expansion of this in the team. So we already see some predictable pathways of usage, which is why we call it mixture of pathways architecture in the existing model. But we're now really scaling this model up to a larger scale, including sharding algorithms and specific deployment algorithms for HPC in a larger architecture to see whether the things we've been doing on the small scale hold true on the larger scale. If you look into the paper in detail, you'll see that the models we've been working with are actually kind of small for now, just because we needed to iterate quickly, and obviously, academic compute sizes can be smaller. The other thing which we are very interested in now, in order to make a responsive architecture, is a new avenue we are exploring actually together with Synopsys. I think Dan Wilkinson is on the call today, joining the group, where we're really interested to see how such an algorithm, which we are so far making responsive to the workload, can also respond to other telemetry metrics that you have on the system. Synopsys has developed an interest in how to capture these chip telemetry metrics. What, for example, is very interesting for us is chip temperatures and network usage statistics, etc. So what is really interesting is that with this dynamic algorithm, it can actually decide what to spend compute on as a function of workload, but hopefully also as a function of the underlying system state. So the system state of the hardware can actually feed upwards into the algorithm and how it is currently deployed. Because we're very interested in this, and we are literally like this weekend now starting to plan this out and how we can get these features in. A couple of ideas already, but probably in a future update we will report on this in more detail. I've talked for a bit, but obviously I want to talk a bit about also the classical co-design that we've been going on, specifically in the context of AstroSim, which obviously has been discussed in this group many times. So specifically, this work is very much ongoing. So I don't have super specific findings for now, but essentially what we've been starting to do is we've been seeing how, if we have different algorithms and compare them with different clusters and different scheduling, how we actually find very interesting patterns between like memory bandwidth, network latency, etc. As I said, not really like super concrete findings yet on this side, but I'm quite confident that for the OCP presentation, we'll have some cool, some some cool findings where we show how the algorithm structure itself can co-evolve, as for example, if memory bandwidth of your cluster is higher or lower, something along those lines. Yeah, we've been finding some interesting relationships, for example, where memory bandwidth, it's not a linear decrease essentially on the cycles needed to run your workload. It's a function of memory bandwidth, but there's these kind of critical points which you might be able to optimize for, and these critical points might have different times for different architecture designs. But yeah, this is very much ongoing. Wish we had a couple of more advanced findings for this, but not today. And obviously the goal for this in terms of the polymorphic architecture and co-design group here is that we actually simulate this on heterogeneous clusters. So we've been playing around this so far, specifically on the network capacities and network topologies, bringing in different heterogeneities on that level, because AstroSim is a bit more advanced on the whole networking level, but we've now started looking into device level heterogeneities too. Cool. So that's all for me and from the work stream. Maybe I thought I made this list of like what our next steps are to prepare for the global summit. So in the first instance, we are properly testing new deployment strategies on large-scale architecture, as I said, with Gabriel, who's on the call, I think. Then using AstroSim, we're showing how new algorithm design parameters can co-evolve with the cluster architecture, both for deployment and fine-tuning of routing. And we are also now working on the specific outline of telemetry as feedback signals in both the simulations and tuning of the algorithm ultimately. So the other goals for this group specifically, I'm obviously in the broader sense of the global summit. I believe Semantica is presenting ahead of me at the global summit, so I'm planning to sync with her next week to get like a nice logical links between the talks. I think it's really nice we get two talks right after another, so we can kind of play off each other's content a bit. And then I believe that Jack suggested that Tushar and Kingshuk might both have a slide to contribute to my overall deck for the OCP Summit, both on the schema and on the AstroSim. I think both of them make total sense in our presentation, so we can work this in. We should find a time to see what you'd like to have in. We can probably do this kind of a bit closer to the actual submission deadline, but yeah, as long as Tushar or Kingshuk give an idea what it is you want to have in, just drop an email and then we find a good place to put that in.
Absolutely.
That's the
Absolutely.
that's
And
the
we are
update from
happy
me.
to do that. Yeah.
Cool. Yeah. Any questions on that?
Yeah, when I looked at your papers, the brain-like processing pathways from models with heterogeneous experts, that looks like it has something to do with the neuromorphic computing or brain-inspired computing.
Yeah, I mean, it depends a bit on how you define neuromorphic, right? I mean, neuromorphic in the classic then is spiking, which we don't do in that paper at all. It's we use a so it's not classic neuromorphic at all. It's actually very much aimed at classical at standard acceleration architectures like standard GPUs, etc. In that specific paper.
Okay, good, got it. Thank you.
No problem. Cool.
You said Daniel is attending?
No, so Dan is out. He's visiting families, obviously late in the evening in the UK. So he's not here. But Gabriel, who's a student in the lab, is now working with me on this. Is I believe on the call. I see his name at least. So yeah, he is.
Oh, yeah, I see.
Yeah.
Good job. That's good.
Cool. Yeah, that's all the updates from my side.
Okay.
Or our side, I have to say, obviously, like this is obviously a team effort. Don't want to, take all the credit.
Hey, Yasser, for your dynamic deployment algorithm, does it require any specific like infrastructure level of capability?
No, not really. I mean, so the stuff that we are working on with Gabriel in the first instance now is not really infrastructure specific. Actually, it works on anything which can deploy matrix operations, because we just use like a simplified transformer to do that. But ultimately, what we are hoping to work on with Dan Wilkinson, actually, there's two Dans in this talk. This is always confusing. Lots of Dans around. We're hoping to get to a state where we can use the actual state metrics of the system, and that will be very dependent on the actual chip you have, right? I mean, the telemetry on current hardware isn't great. which is why actually we haven't dabbled into the system too much. We always wanted to, but now there seems to be an outlook that maybe it will get better. So we are super excited for that. But yeah, it will be very hardware dependent ultimately.
I see. So for the telemetry type of support, does it only require a chip level, or you need more kind of a system level, or even cluster level type of support?
I think very local chip level stuff would be fine in the first instance. But I don't want to make too specific statements because frankly we haven't fully worked this out yet. And maybe Dan has more specific opinions on this. Yeah, just starting to think about this really.
I think you're right, Yash. And hi, everyone, by the way. This is my first week at the group. Obviously, anything that comes out of the chip, you've got thousands of chips, and you need to bring it all to some central point in some sensible way that you can actually make use of that. And also, what's relevant is the timescales Yash referred to. Because with telemetry, you've got stuff that you could react to very quickly, or if you take a long time, it's too late. You can learn from it, so that whole timescale thing applies. And the longer the timescale gets, the more you have to worry about archiving it and all that sort of thing. So I think the answer is, whenever you're talking about a big cluster, the telemetry is coming from lots of devices. Those devices are very diverse. They don't implement telemetry in the same way. So I guess the first order of business is, what can you rely on as sort of a lowest common denominator you can get from those devices? It's quite hard, I think, and probably inadvisable to try and sort of architect for any specific devices and try and keep things general, at least while we explore what's possible and and what kind of telemetry or timescales is actually useful for this kind of activity.
So Dan, this is Jay. So do you know what you're going to use the telemetry for? What's the end application?
Well, like Yash said, it's essentially the state of the system at any one point in time, right? So the telemetry from the devices give you everything from temperatures through to aging statistics, the counts of reliability or unreliability of individual memories in the system, but also things like performance counters, bandwidth counters, whether those are in networking devices or compute devices. So those performance counters will be giving you some sense of utilization or efficiency. So that's part of the system state. And if you can use that information, if you can relate when the workload makes a demand, then a certain amount of time later the state looks like this, and you can start to, at a high level, at a coarse grain level, probably start to predict some of that. Then you can potentially use that. Obviously, it's complicated.
Got it. Yeah. No, okay. So the reason I was asking, because there's a lot of work which has gone in, and a lot of work, I'm the key author of that. But when we say telemetry, the end application, typically we look from the workload placement point of view, congestion control algorithms, multipathing, if it's a multi-rail, multi-plane design, load balancing across the planes. So that's what I was thinking. And, the telemetry of interest there is, what's the base RTT to begin with? Is there a min-max bandwidth for a given path within the scale up or a scale out, etc.? But I think you are looking more at a system level, because there we don't think about temperature, etc. Right?
Well, yeah. I mean, I think that if you just stick to the workload statistics, performance statistics, obviously all that stuff you mentioned is there in terms of the networking and the wider infrastructure. But in terms of what's going on the compute side as well, your cache misses or the degree to which you're utilizing the memories attached to those devices, that kind of thing. Because obviously when you start playing around with how you place stuff, and Yash mentioned earlier about all that sort of pathway stuff, and you're looking at different hardware architectures in that slow time scale, but even in the fast time scale, when you've got you're trying to do batched inference over many users with different size queries and different caching requirements, that's all going to affect stuff, right? So if you can get visibility into how the decision, the scheduling or placement decisions you make affected actual performance. That's good. That allows you to learn something. And if you, then the next step is to look at, the next step beyond that really is to look at like the system state in terms of its environment, which is probably too fast for much of what we're talking about here. The timescale is too quick. But that's not to say you can't learn from it after the fact, right?
Right. No, that makes sense. So I understand now. So you are looking at much. I was looking at a much lower level, where the actual spawning of the workload or the placement or the distribution of the when we do the sharding, right? So the data is placed on a given path or a given GPU, and that you are absolutely right. That telemetry which we collect, it's almost at a per packet basis. So it goes into, sort of in a nanoseconds to very low microsecond granularity, right? So, but that's consumed at a lower level, and I think what you're saying is at a higher level, you still need a bunch of other telemetry for system to work.
Yeah, I mean, we can, we can histogram stuff. You can filter it. You can process it so it is appropriate for whatever time frame or time scale is meaningful for the framework we're trying to execute. So just because it's produced potentially at fairly high bandwidth or produced instantaneously on the devices in the system, that there's lots of ways obviously to filter that and curate it and boil it down so that it basically gives you a summary, right? And the question I think would be interesting to look at with Yasha and his group is, what kind of summaries are relevant? And how do you take that data coming off the device and put it down, in open telemetry or something to give you actionable information about system state, whether it's performance state or environment state, and just start thinking about what might be interesting there. And then really, Synopsys' long-term interest there is to try and pick out, what kinds of telemetry information is most relevant to this type of thing, and see whether we can't, in the fullness of time, start supplying some solutions to a whole load of chip designers and infrastructure makers that help to produce this telemetry in ways that's hopefully consistent across many devices, because the problem is these devices are all different in this regard at the moment. So the more you can unify that, the more it's going to enable, I think, this kind of activity.
Makes sense. Thanks.
Cheers.
Okay, thanks, Stan, for good discussion. So we already went through the update from Keysight. So maybe Jay, you can provide some network update.
So, I think my focus was I was trying to put a white paper with Jack on the scale up, and that landscape is moving so fast. So, and there was a paper which I added a lot of content. It's now that information is stale. Site-wise, Wafing, we have done a contribution. Now that's coming as a Broadcom contribution, not just as mine, which we call as SU, right, which is a scale-up Ethernet. And that's exactly what I was trying to capture in the paper. So what I was thinking that I think I'm going to shrink that paper, the white paper with Jack and myself and others are working on the scale-up, and create a reference concept which eventually will point to the scalar, the SU spec, which is already is contributed in OCP. So that's something which I have to talk to Jack, because the information which is there in the white paper today is now stale, right? It's a little bit old. I mean, this field is moving so fast. So that's something I have to work with Jack on it.
Okay. Do you have a pointer to the white paper?
If you do, just search OCP SUE. You will let me put it in the chat. Just give me 1 second.
OCP SUE. Okay.
You will see, various places that. Let me just share the Broadcom
Sure.
pointer, and you can download. It's formally contributed to OCP, and it's going in the OCP networking track for whatever reason. And let me see if I can find it on the OCP website. It should have a corresponding link on the OCP website too. I'm just trying to find. It may not be live. It's on the OCP group. Let me see. It was discussed on a monthly call by one of our marketing person. I'll put that link as well.
Does this have anything to do with the UEC? Or?
No, this has nothing to do with UC. This is OCP. In UEC, there is some. It's a, there's so many. That's why I was saying this is such a fast-moving space. In UEC, what we are working is called as ULN. It's called as Ultra Ethernet Low Latency Network, right? So that's called as ULN. Essentially, it's a scale-up. That's a little bit of a different spec, and that's still in the works. But eventually, you will see that some concept of UA link, which can be encapsulated in an Ethernet frame, they all will converge eventually, right? But right now, they all are moving sort of in independent spaces, but there are common people who are working within all these forums. So you will see eventually they will all converge in one form or shape.
So Jace, well, you also got a talk at the summit, right? So are you presenting that specification, or what's your plan?
Yeah, the presentation which I'm doing, what's happening also in the industry, we are realizing that this boundary of scale up and scale out is getting a little blurred, and that's just because of the investment. And people are saying that if I can create a scale up topology, which let's say scale ups to 2K GPUs, right? That might as well be used for scale out. The problem with that approach which comes is that the fundamental characterization of the workload for the scale-up fabrics versus the scale-out fabrics is very different. One is memory semantics, one is network semantics, right? So it puts a lot of challenges in terms of the entire stack. How do you do the topology discovery? How do you figure out what kind of characterization you need for that topology so that you can feed into either the data movement protocols like Nichols or whatever is there. And then you also need that information to be bubbled up to Slurm for the workload placement and various algorithms. So my topic is a little bit more focused on those areas which are not yet solved, and it's basically to trigger the conversation. And there are people looking from various angles on that problem space.
Yeah, that makes sense. I also see that Kevin actually joined, so maybe Kevin can give his update. I know he was on the list.
Jay, I have a question, Jay. There is a new group work stream created by Broadcom. It is led by Lowell Lamb.
That's different. That's different.
Okay, that's good. That's fine. Yeah. That's different. Okay.
Yeah.
Thank you.
Yeah, I missed the calendar entry for this meeting, so I'm sorry I'm late.
Okay,
yeah,
so
that's all update I have. So I have to talk to Jack and figure out that how do we work on it? Do we kind of just refer to the OCP SU spec for a scale up? I'll talk to Jack that how do we want to proceed on that.
Yeah, sure. We probably can have offline discussion to see how we proceed.
Right.
Okay, sounds good. Victor?
Yeah, can you see my screen now?
I Okay, can see it now.
Yeah, I bring not a solution, but a problem. So this is the one initiative that I participated in the Linux Foundation called the Data Ops Initiative. So we're enabling metadata-driven AI multi-task orchestration, which means you can potentially orchestrate your job based on the data catalog, which goes almost to the semantic layer, which means that you know what's the detail of the job and what does it mean to be slow and what's the implication to the business. So in order to do that, we have something that's missing, I think, from the hardware side. Need your help here. And one of the solution, not solution per se, but the prior art is the Oracle Weight Interface, which I brought up before. And Oracle has this thing called SQL Trace, which is very nice, detailed. You can even run in production. However, it's too heavy and it's also not real time. And the way Oracle does it is to do kind of aggregation. I'm not going to go in details here. And then, so this is the part I'm going to go discuss in the Checker team on how to make what they have done so far into something that's more real time. And then what I really want to update is this thing. This is what I discussed in the Julia community. In my opinion, they have done the best when it comes to software hardware co-design, all the way from the actual hardware GPU programming to the actual language design. And this is the answer. So there's one simple requirement we need from data ops perspective, right? Not data ops, any job. The question is, how much time has been captured? That's the job spent running on GPU or CPU or something else. The answer is, at this point, there's no solution. Remember, this is all GPU experts, so they know the details. So at this point, the only way to do that is to capture the start time, launch this kernel, in this case, the scientific kernel, capture the time again, which is the mid, synchronize it, capture end time, and then calculate the amount of time spent on CPU and GPU. And this is the reason why this is not possible, because most of the library are not open source. And based on this conversation, looks like some of the library from AMD are open source. But in order to be able to capture all this, there need to be some kind of either API open source that's available to capture those details and to be able to do those kind of aggregations that's available for the data ops to be able to run real time, get feedback, and schedule to the right place. That's all I have.
So, did you look at a scale, the semantic layer of at scale, which got acquired by Meta?
No, I did not. What is it about? So the problem here is the library, right? So for example, the NVIDIA, AMD, Intel, and everybody whoever have provided hardware, CPU, GPU, those matrix is not available for, like, for example, Julia or Python developer. So for example, the current trace that AstraSim, not AstraSim, but the Checker Trace based on is just like SQL Trace. It's similar to Oracle SQL Trace. That's great. That give you information. You can do batch job, do that. You can even do design. But if the workload and hardware is static, that's good enough. But if you want to do it real time, like what we're trying to do in polymorphic architecture, do it in real time. That's similar to the requirement we have in the data ops world. Right? We need something real time, something that's lightweight and aggregate real time as well, to be able to give that feedback to the job, to make decision on where the job fits.
Are you looking for a sort of more virtual environment which is giving you feedback about how things are running?
I think this is really something that needs to happen in the ecosystem. Probably probably here even, just how to expose those matrix from those libraries, even if the whole library is not completely outsourced, open sourced. at least there's some ways to expose those matrix to be available, to be aggregated in this way, and real time to let me know. So this is a really simple question, right? But even this is not possible with. I mean, it might be possible for one computer hardware, but if when I do orchestrate different hardware in a polymorphic architecture, there's no way for me to tell how long my job is running using CPU versus CPU versus networking, etc.
Okay.
So basically, you want to have a more fine-grained breakdown for the different part of a data moment, right? So either parsing time or transfer time. But with your existing, you see like the skeleton you listed here, is this sufficient for you, or you feel like the CPU time or GPU time maybe
This
kind
is
of
a great.
aggregated from multiple threads rather than a per thread basis?
This is a great start, because if you look at the Oracle weight interface, there's 13 weight classes. Among them, CPU, memory, there's no GPU, right? There might be some GPU now, but at that time, there's no GPU. But as long as you can tell me how much time is spending on CPU, GPU versus networking, which type of networking, is that within SoC or external networking, that will help a lot.
What about the question, okay, let's say how long you took on CPU versus GPU, and the GPU is taking longer. Do you need to know why? Like either it's because the workload was put on it, wasn't optimized, and now you put it on in a different way, so the memory bandwidth to compute ratio is different, or it's because it got hot and that GPU throttled back. Some GPUs throttle back, some don't. What about that?
Yeah, that's the beauty of Julia. Julia is built from ground up. People who build Julia directly do the GPU programming and then turn back and build the actual language itself, right? In the Python world, it's hard because the people who do the actual Python library design and PyTorch design is different from the scientists and users, right? That's going to change. There's a new thing by Chris Ledner. It's called Mojo, which is similar to Julia, which will give you the visibility from high-end users like scientists or data scientists, AI ML trainers, all the way down to GPU. But that's in the future. That's not available yet. So I have. This is just a problem. This is not a solution. This is a problem that bring it up. So in order to solve this problem, I think definitely need to have some kind of a way to gather this matrix, even without open source, gather the matrix, aggregate it in a way, and then something like PyTorch need to aggregate it and to be available to higher up layers.
Yeah, so let's say if you do have access to those telemetry inside the GPU, is that sufficient for you, or you feel like because you may have a multiple process doing a kind of a round robin execution, so the even current like performance counters won't be able to provide that level of breakdown for you?
If you look at the Oracle's way to tuning, because my expertise is Oracle database tuning, done that for 30 years. So if you have a high level weight class, meaning it's CPU versus GPU versus SoC memory versus networking memory, as long as that, even if it's not exactly to the details, it's already very helpful. The problem is even that is not available at this point.
I see.
But NVIDIA Insight Systems may provide some profiling tools, which can tell you.
Exactly. So many tools, including NVIDIA and Intel, AMD, all of them have some sort of that. And there are two problems for that. Number one, there's no uniform matrix. That's the one problem, no standard. Number two, it's not aggregated. It's trace file. It's not matrix. It's real time. Because once you imagine Oracle SQL Trace, right? If you turn it on, Oracle's claim is the 5% performance degradation. But what the problem is, it's going to fill up wherever you place trace file really quick. It's going to be terabytes pretty soon.
But if I have a task and you want to know how much your time is spent in CPU and versus GPU, NVIDIA Insight systems can do that, right?
Not in the aggregated way and not in the way that
What
can
do you
be.
What do you mean by aggregated way?
So I need to tell. So basically, let's imagine, like, let's say it's a system. It's a system, NVIDIA-based system. I ask it, like, my job is running, right? Can you tell me in the past 10 minutes, how much time is spending running on CPU, how much time is spending on GPU, and how much time is spending moving data around in the remote network versus, in the SoC? Can you tell me that?
You're right. That's new.
But there's a lot of monitoring in a regular sort of Linux environment.
Yeah, all of that is nothing is available. Again, this is this is the people who actually have been designing the language. Julia, that they
Yeah,
told me.
but you can, when you're looking at code, it's a big graph essentially. And you can pull the graph apart and look at the pieces in between, which would be, message passing in the network and stuff.
Yeah, it
So,
might be
so this is something
possible.
where you can actually sort of tweak it so that you're actually tracking those things in the network, which are outside the software itself.
Yeah, look forward to a solution from you in that area. Yeah, there's no such a solution at this point.
Well, you kind of want to know, is the application running or is it stalled?
Exactly.
Because the power's kind of flat anyway, so
yeah.
your efficiency is how much of the time it's running.
That's another beauty of it. In the Oracle wait interface, there's one class called idle event, which means it's hung.
Yeah.
Even if but the problem is when it's hung, sometimes multi-threaded, right? Which part of it's hung? Those kind of a drill down detail, of course, is nice. But at this point, not even that. We just need to know overall the job, the whole system, which wait class is spending the job is waiting on, whether it's moving data or doing training or inferencing. There's no such information.
The question is, can you infer it somehow?
A lot of manual ways of doing it. There's no systematic standard way to provide that matrix.
Did you look at Intel vTune profiler?
All of them, the only open source of way, my understanding is the media. I'm sorry, AMD to some extent. Yeah, we can talk offline, but so far I don't think so. There's nothing available.
I think an idea came to my mind now. There is a consortium, maybe you heard of it. It's called OpenXLA, right? And the OpenXLA project, it is really one of the, you heard of it. They may look into this issue.
Hopefully, yeah. So far, I have not been able to find any community that handle this issue.
But are you a member of OpenXLA?
If you let me know, I'd love to ask a question there.
OpenXLA is a big consortium.
Yeah.
They deal with all sorts of things regarding acceleration, profiling. So you might need to, Oracle may be already a member of OpenXLA.
No, I'm ex-Oracle. I'm not Oracle. I'm independent right now.
I mean, one of the things you can do in this space is try and get sort of versions of things running on FPGA where it's instrumented, and try and align what you're learning from the FPGAs with what you're seeing in the uninstrumented.
Yes. As a matter of fact, in the RISC-V community, there's an FPGA project that's sort of doing similar thing what's being doing here, which is kind of polymorphic kind of a orchestration, different kind of hardware that their effort going on right now. But that's huge. That's number one. That's future. Second is FPGA. It can probably play.
The thing is, you can stick a model of a GPU or whatever processor you like in an FPGA.
Yeah, it can play the front end orchestration portion, right? It may be even to run the Yasser's the algorithm, but it's still the stuff still need to run on the fast GPU, those hardware, right?
What I'm saying is you can digitally twin the GPUs into an FPGA environment where you can actually see the behavior properly.
Oh, I see. Yeah, sure.
And then what you want to do is align the behavior you see in the real stuff against what the FPGA is doing, which has got the instrumentation, and then see what you can infer.
Yeah, the good idea. But the problem is that it's not me. It's the whoever is building either the PyTorch libraries, or the hardware provider themselves. They need to provide that matrix.
Well, as you said, the RISC-V guys are doing open source things. So you can play with the open source RISC-Vs or the vector extensions and things like that and see how they behave. I mean, it's one of the things you want to do in the RISC-V community is work out what are the extensions that are useful for my particular application.
Agree.
Yeah, Victor, I'm not sure if you, let's say, if you define certain APIs to specify what type of information you want to collect, and then using the existing performance counters or those kind of telemetry, whether you are able to deduce the level of information you need.
Well, I think there was a thing before where you collect too much data if you try and log it, so you need a processor which is doing it internally.
Yeah, we can definitely I said I'm more representative user of what your guys are doing. So definitely we can probably start to capture those kind of requirements from a higher level, right? In data ops, for example, which I participate, we can capture what matrix needed to be exposed so that we can make decision based on the data catalog and etc. Yeah, but the right now is just nothing's available. So we were just what we've been doing on the data job scheduling side. We're basically doing bin packing. More like afterwards, we say, okay, this job has not been running very well. Why did kill it? And then now we get stock open. Let's put something else. That's basically what the job scheduling is right now. There's no, okay, this is actually slow because it's supposed to be running on GPU. It's actually on CPU, and so those kind of things is only possible with some real time matrix.
Okay, so we already have 11:06. So thanks everyone for a good discussion, and we'll just wrap up the meeting and have a great weekend.
Thank you very much.
Thank you.
Real
Thank
quick,
you.
can I get a
Victor,
link of the past minutes?
Oh,
Yeah.
oh, sorry. Yeah, go ahead.
Victor,
My
we can
question was, can I get a link for the past meeting minutes or any procedure?
We have everything in the OCP drive. I don't know if you have access. I can give you the driver. Let me paste the link here.
Okay, thank you.
You can just click on it. If you don't have access, I'll grant that to you.
Thanks. That works. I got it. Thank you.
Okay, great. Thank you.
Thanks.